So now we'll discuss Fraunhofer diffraction for a single slit. Okay. So Fraunhofer diffraction means both the source and the screen are effectively at infinite distance from the aperture. So as you can see that the parallel beam, so as the source is at infinite distance, the parallel beam which is incident on the ray of beam of light which is incident on the aperture will be parallel. So as you can see that the this beam of light is parallel and it is monochromatic, and after being diffracted from this aperture, they are focused on the screen which is placed at focal length of this lens. Okay, so that the screen is also effectively pushed to infinity with respect to this aperture. So here you see we have a very narrow slit AB which has a width of A. So the width of the slit is A. Okay, and this parallel beam of light of monochromatic light of wavelength lambda, the incident on it. Okay, and the light passes through this. After passing through the aperture, as the dimension of this wavelength of the light is comparable with the dimension of the aperture, they will suffer diffraction. Okay, now you see, so we can say that the width of the slit AB is the parallel beam of light of wavelength lambda incident on the slit. Now the center of the screen XY. Okay, so suppose this is the screen XY. Okay, its center of the screen is O prime and the center of the slit is O. Okay, so the light rays, you see, when suppose the light ray which passes through the O, this point O will act like a source of secondary waves, okay, which will send out secondary wavelets in every direction. So in one such direction, one ray passes along O prime without any deviation or diffraction. Okay, similarly, every point, if we consider another point source at A and at B, then the point source at A will also act like a secondary source which will send out secondary wavelets in every direction. Same goes for the point source at B, which will send out secondary waves in every direction. So as a result, different rays will be diffracted in different direction by different angle. Okay, so you see there will be some rays, okay, for every point on this slit. Okay, every point on this screen, on this slit, there will be some rays which will suffer no deviation or diffraction, and they will pass parallel to O prime. Okay, and after passing through the rays, they will be focused at O prime, which is the center of the screen. Okay, and there will be some rays which will be diffracted by an angle theta, like these rays. Okay, which are diffracted by an angle theta, and there will be other rays which are diffracted by some other angle. Okay, and all these rays which are diffracted by the same angle theta, after passing through the rays, again they will meet at the same point. Okay, suppose this point is P, which is lies on the screen XY. Okay, so the rays which are diffracted by the same angle, after passing through the lens, they will be focused at the same point. They will meet at the same point on the screen. So now we'll find the, so as the rays they meet at the point P, they might so they will superpose, all the rays will superpose. Okay, and depending on the path difference between all the rays, we can determine the what will be the intensity at point P. Okay, so now we'll find the which will be the general expression. So we'll find the what is the intensity at any point P on the screen. Okay, for the rays which are diffracted by which are diffracted at an angle theta. Okay, and the expression will be called the intensity distribution function. So here we have the diagram for the intensity distribution function. As you can see that it is the same diagram. Okay, and we have given some new notations, like so here we have these rays which are diffracted by an angle same angle theta. So all the rays are diffracted by the same angle theta, and after passing through the lens, they meet at the same point P. Okay, So here we are showing two extreme rays at the upper end of the slit A and the lower end of the slit B, and the ray which is coming from the central point of the O, central point of the slit O. Okay, now along the this vertical direction of the slit, we have taken it to be z-axis. Okay, and this center of the slit O is, suppose it is like the center of the our coordinate system. Okay, so its coordinate is 0, 0. and as the width of the slit is A, so what will be the coordinate of A? Okay, it will be 0, a by 2, and so above O it is the positive z-axis, and below O it is the negative z-axis. So the coordinate of point B is 0, minus a by 2. Okay, and so this is the z-axis, and any axis, okay, suppose this axis or this axis which is perpendicular to the z-axis can be either x-axis or y-axis. Okay, so now suppose the intensity of the incident wave front which is incident on this slit, as the width of the slit is very narrow, we can assume that the intensity across the slit is uniform and it is equal to c square. Now if the intensity of the incident wave front is c square, then the amplitude will be root over c square, which is c. Okay, so we can say that the amplitude of the incident wave front across a slit of width is c. Okay, so as now we know that according to Huygens principle, each point on the slit acts as secondary source, okay, which send out secondary waves in every direction. We can assume that each secondary source which is sending out secondary waves, each this secondary waves has an amplitude of c by a. Okay, so now suppose what will be the equation of such disturbance or such wave? Okay, so it will be similar to a wave equation. Disturbance means this waves, okay, any kind of disturbance, because they are sending waves through the medium. Okay, they will create some disturbance in the medium, so you can use the term disturbance. Okay, so what will be the equation of such disturbance as secondary waves at every point on the slit? Okay, which is given by, suppose y equals to c by a to the power I omega t. So y is the displacement of the particle, okay, in the medium which are on the slit, okay, due to this secondary waves. Okay, that is so there is some displacement of the particles. That's why we can, that is the particles they are disturbed. Okay, because now they are oscillating. So that's why we can use the term disturbance, which is given by c by a to the power I omega t. Okay, now suppose this OP is equal to R0. Okay, then this CP is equal to R. So what is C? So over here we have taken a very small elementary length on this slit, which is dz. Okay, so it has a dz is the elementary length at C. Okay, so this CP, if we don't consider this deviation, okay, and because theta is very small, it is almost like a straight line. Okay, so OP is R0 and CP is R, and dz is the elementary length at C. So the equation of the disturbance, okay, at every, as we have said that at every point on the slit is given by y equals to c by a to the power I omega t. Then the disturbance which starts out from c, it also obeys this equation, which is y equals to c by a to the power I omega t. Okay, so then this disturbance after passing along this line, okay, and then reaching point P. So here what will be the disturbance at point P? Okay, so now as this wave has traveled some distance, there will be some extra phase difference, or because it has traveled an extra path. Okay, so now the phase of the wave will change. Okay, so at first on the slit the wave, the phase of the disturbance or the wave was omega t. Now the wave has changed because now the wave has traveled the length Cp. Okay, then it has reached the point P. So now, so what will be the equation of the wave now? Okay, so what will be the equation of the secondary wave emerging out of the, so first of all, what will be the equation of the secondary wave emerging out of the point source on which is on this. Okay, so the equation of the secondary disturbance on each point of the slit is given by y equals to c by a to the power I omega t. Okay, and suppose on dz it is dy, which is c by a, for each point it is c by a to the power I omega t. Then it will be the length of the element, which is dz. Okay, because for each point it is c by a e to the power I omega t. So for a dz length it will be disturbance due to each point multiplied by that much length, which is dz. Okay, now the waves which are starting out from dz has this much disturbance. Now they travel a length of Cp. They travel a length of Cp to reach point P. Okay, so say they have traveled an extra path. So now there will be an path difference created, an additional path difference which will change the phase of the. So here omega t is the phase. So now the phase of the wave which reaches the point P from dz will change.